Hi, I'm going to be talking about our paper on exploring and learning in sparse linear MDPs. This is joint work with Ankur Moitra and Drew Rohatgi, and I'm Noah Golovich. This talk is going to be on the topic of reinforcement learning, which describes the setting in which a learning agent interacts with the changing environment over a series of episodes. The learning agent's goal is to learn enough about its environment by exploring the states in the environment so as to find a good policy, namely one with near optimal expected reward. Reinforcement learning has numerous applications, such as in game playing, robotics, healthcare, and recently, ideas from reinforcement learning have found applications in training large language models. Typically, reinforcement learning is modeled through Markov decision processes, or MDPs. Now, a finite horizon, in this talk, we're going to study finite horizon Markov decision processes, which are tuples of the following components. First of all, there's horizon H, which is a natural number, an action set capital A, and a state set capital S. There's an initial state distribution D, which is a distribution over states, as well as a transition kernel P of S prime given SA, which gives the probability of the environment transitioning to S prime, given that we're in a state S and the agent takes action A. Finally, there's a reward function R of SA, which gives the agent's reward, given that it's in state S and takes action A. A trajectory in an MDP consists of capital H steps. Initially, an initial state S1 is drawn from the distribution D, and at each step little h from 1 to capital H, the agent observes its current state SH, it chooses an action AH according to some policy, and then the environment transitions to a new state SH plus 1 from the transition kernel P. The agent also receives reward R of SH AH according to the reward function R. Now, as I mentioned in the previous slide, the way the agent chooses its actions is according to a policy, which formally speaking is a tuple of mappings pi1 through pi capital H, where each pi little h is a mapping from the set of states to the set of distributions over actions. Capital Pi denotes the set of all policies. The value of a policy denoted by v pi is simply the expected value of the total reward the agent receives over a single trajectory. So it's the sum from little h equals 1 to capital H of R of SH and AH. The optimal policy pi star is simply a value maximizing policy. The agent's goal is to find some policy pi hat whose value is near optimal, namely so that v pi star minus v pi hat is small. And the way it does this is in the following online setting. The agent interacts with the Markov decision process over a number of episodes. In each episode, little t, the agent chooses a policy pi t, it executes it, and then it observes a trajectory consisting of states, actions, and rewards drawn from the policy pi t. It then uses that data to choose another policy pi t plus 1, and it repeats this procedure for a total of capital T episodes. At the end of these capital T episodes, the agent outputs some policy pi hat. Now, we'll measure sample complexity of this procedure via the number of episodes, capital T. It's a standard result in reinforcement learning theory that if the number of states or actions is relatively small, say bounded by a polynomial, then there's well-known computationally and statistically efficient algorithms for learning a near-optimal policy. However, in many of the applications I mentioned in reinforcement learning, such as in robotics, or in game playing, the number of states is going to be extremely large. For instance, in the game of Go, the number of states is exponentially large in the size of the game board. And in robotics, there's often a continuous state space representing all possible configurations of a robot. As such, it's a very important and natural goal to come up with natural classes of MDPs which have a large or even infinite state space, but at the same time emit sample-efficient algorithms. And in light of this, there's been a lot of examples in the past 5 to 7 years that people have come up with which meet these two requirements. These include model classes of MDPs, such as block MDPs, low-rank MDPs, linear MDPs, and many other examples which are listed here. However, many of these works suffer from the following shortcoming. For many of these models, the existing algorithms that obtain sample efficiency often ignore the computational aspect of the problem. And moreover, even when computation is considered, these works rely on certain oracles that can solve computationally intractable subproblems. And in light of this issue, it's natural to augment our requirements with a third, namely that these natural classes of MDPs have end-to-end computationally efficient algorithms. In particular, we don't want any reliance on unimplementable oracles. And when we add this third requirement, most of these existing examples fail to meet it. And in fact, the only one that does is linear MDPs, which will be the topic of this talk. Now, I'll note that by adding this third requirement, namely requiring computational efficiency, we give ourselves a window into reasoning about which algorithmic ideas can lead to computational efficiency in reinforcement learning. And ultimately, the hope is that some of these algorithmic ideas will augment our toolbox of possible techniques, and perhaps some of them will find use in practical RL algorithms in the future. Okay, so let me now define linear MDPs. An MDP is called a linear MDP if there are feature mappings phi from the state and action space to RD, as well as a feature mapping mu from the state space to RD, so that the following holds. We want that for all state action state tuples, namely SAS prime, the probability of transitioning from S prime to S prime, given that we're in state S and take action A, is the inner product of phi of SA and mu of S prime. We also require the reward that we receive at state S in action A is the inner product between phi of SA and some coefficient vector theta, also in D dimensions. Another way of saying these requirements is that the transitions and rewards have to be linear in the features phi. Now, typically in the literature, it's assumed that the feature vector mu is unknown, but that phi is known. And under this assumption, the work by Jin, Yang, Wang, and Jordan showed that there's a computationally efficient algorithm for learning a near-optimal policy in linear MDPs, whose time and sample complexities scales a polynomial in the feature dimension D and the horizon H. Now, this is a very nice result, but there's one important question which remains, and that is, where do the features phi come from? Somehow the features phi have to capture all relevant information about the state action tuple for determining the transitions at each step. And in general, this could be a pretty challenging problem given that we don't actually know the transitions. So let's consider one naive approach for defining phi. The idea is essentially take a kitchen sink consisting of all possible features that we could have, and I'll denote these by phi1 of SA through phi d of SA. So you should think of D as being extremely large. For instance, some of these features could be nodes representing the intermediate layer of some pre-trained neural network, which may be able to extract useful features. Another more classical approach is to use certain heuristics based on domain knowledge of the problem. Now, because the number D may be extremely large, we don't want our sample complexity to depend on D. In order to ensure that this is the case, we're going to have to assume that only a small number K, which is much less than D, of the features are actually useful for determining the transitions. And this leads us to the definition of a K-sparse linear MDP, which is a linear MDP for which there's some unknown subset of features, which I'll call J, of size K, so that for all states S, the support of the feature vector mu of S is a subset of J. We also require that the support of theta is a subset of J. So to understand what this means, let's consider the definition of linear MDP shown on the right here. That the support of mu of S is a subset of J means that the only coefficients of the vector phi of SA which matter in determining the probability P of S prime given SA are exactly those positions indexed by the subset J. And the same holds for the reward R of SA. And so this exactly captures our intuition that only a small number of features be useful. I'll mention that there's also some additional norm constraints on the feature vectors mu and phi, but these are relatively standard for the problem. Okay, so given this definition of a sparse linear MDP, the main question that we ask is as follows. If we're given a number of episodes of interaction which scales the polynomial k in log d, then can we efficiently find a near-optimal policy? And by efficiently, I mean an algorithm that takes poly d time. Note that we're going to need poly d time in any case, because we need, for instance, linear time in d to simply read the feature vectors. The number of episodes of interaction, however, should be much, much smaller than d, representing the fact that we don't have that many samples. We also want the dependence on the number of actions as well as the horizon to be polynomial. So our main theorem is a positive answer to this question. What we show is that there's an algorithm which takes a number of episodes of interaction, which is polynomial k in log d, and then it outputs an epsilon optimal policy with probability 1 minus delta. And its running time is a polynomial d as well as the other parameters of the problem. I'll remark that the best prior result for getting the sample complexity scaled had computational cost, which scaled as d to the k, so it's exponential in the sparsity k. And this was obtained by the technique of global optimism, such as via the Olive algorithm. I'll also note that the polynomial dependence of sample complexity on A and H is necessary. And moreover, our algorithm can be thought of as an analog of the lasso algorithm for the prediction task in sparse linear regression. But one difference between our result and a lot of results in sparse linear regression that use the lasso algorithm is that our result does not require any restricted eigenvalue condition or well-conditionedness assumption on the covariates, namely the feature vectors. And this is in contrast with some of the prior work on reinforcement learning, which did make such assumptions. However, those assumptions had to hold with respect to any policy, and therefore were extremely strong in the context of reinforcement learning. So a main feature of our result is that we don't have to make any very strong well-conditionedness assumptions. I'll also remark that similar to sparse linear regression, our result also holds under a more general analytical notion of sparsity, namely bounded L1 norm of the feature vectors mu. Okay, so in the remainder of the talk, I'm going to discuss an application of our main result, namely to learning block Markov decision processes. Now, the motivation behind block MDPs is to perform our reinforcement learning in environments with rich observations but simple dynamics. So for instance, consider the task of moving a table from one part of the room to another part of the room. The underlying physical dynamics of the system are very simple. There's solid bodies and there's not that many of them, so we may be able to expect to represent it with a relatively small underlying state space. However, the actual observations the robot sees, which may be via cameras, can be extremely complicated. For instance, there's a window in the room, there's a TV in the room, someone could turn on the TV and start flipping between channels. All of these create extremely complex observed dynamics, which the robot has to somehow filter out so as to learn the underlying latent dynamics of the actual physical system. And this leads us to the definition of a block Markov decision process, which is meant to model such an environment. It's similar to an MDP with a horizon, an action set, and an observed state set, but there's also an unobserved latent state set denoted by Z. Now, how does a block MDP work? There's an arbitrary MDP on the latent state space, which is defined by transitions, I'll denote by tilde P, and rewards, I'll denote by tilde R. Additionally, there's an state emission distribution, which tells us, given a state Z, what's the probability of observing each observed state, little s. We denote that by Q of S given Z. In order to make learning a block MDP tractable, we have to make the following assumption of a decoding function, rho star, mapping from the observed state space to the latent state space. And this satisfies the following property. With probability 1 for an observed state S, drawn from the distribution of Q of S given Z, rho star decodes S back to Z. And moreover, the transitions and rewards in the observed state space factor through the decoding function rho star. So you can think of a block MDP as being somehow analogous to a hidden Markov model, where each observed state, or each latent state, produces its own distinct set of observed states. And moreover, the distributions of these observed states given latent states are conditionally independent given the latent states. Now, it's typically assumed that the latent state space is relatively small, so we're okay with bounds that scale polynomial in the size of Z, but that the observed state space S is large, so we don't want polynomial dependence on S in our bounds. Now, in order to get such a guarantee, we have to make some assumption about the decoding function rho star. The typical assumption that's made is that there's some known class of decoders phi, consisting of functions mapping from S to Z, which contains the true decoding function rho star. Existing work on this problem assumes some sort of oracle for the class phi, which I'll discuss more in a moment, and they get sample complexity, which depends polynomially on the size of this latent state space, as well as log of the size of phi. The issue with some of this work is that for essentially any known class capital phi, the oracles of these papers are not computationally efficient. And this is in some sense analogous to the issues I discussed early on in the talk. Now, there's multiple reasons for this. For instance, some of these oracles need to handle noise, whereas the only known efficient algorithms only deal with the noiseless case. Also, in some cases, the works require a proper learning oracle, whereas we only know efficient algorithms for an improper learning algorithm. And in light of this, a very natural question is, what is a reasonable structure for the class phi, which enables computational efficiency? And as our main application of sparse linear MDPs, we give an answer to this question. In particular, we consider the class of NK decision tree block MDPs for positive integers n and k. This is the set of all block MDPs, which satisfies the following. The state space S is all length n bit strings, and the latent state space Z is a set of integers from 1 to k. You should think of k as being some polynomial in n. The class phi consists of all depth log k decision trees whose leaves are labeled by elements of the latent state space Z. So to visualize this, recall that such a decoding function in phi takes as input some state S, which is simply a bit string. Each node of the decision tree conditions on some position in S. We move to left if it's 0 and to right if it's 1. After a set of log k such steps, we end up at the leaf of the tree, which is labeled by the output rho of S for the corresponding decoding function rho. This is an integer from 1 to k. Okay. So what our main result shows is that the set of NK decision tree block MDPs is tractable. In particular, there's an algorithm that after polynomial and k log n and the other parameters, episodes of interaction with an NK decision tree block MDP, it outputs a near optimal policy with high probability. And moreover, the running time of our algorithm is quasi-polynomial, namely n to the log k, as well as polynomial in the other parameters. The proof of this result is pretty simple. We just remark that NK decision tree block MDPs are actually sparse linear MDPs in a number of dimensions d that's quasi-polynomial. And I'll note that the previously known best running time in order to get poly k log n sample complexity scaled exponentially in k, namely n to the order k. And this can be obtained by, for instance, running the Olive algorithm. So we get a improvement from exponential to quasi-polynomial time. Okay, so in this talk, we've discussed the first computationally efficient algorithm for learning a near-optimal policy in sparse linear MDPs. And I've also discussed the applications to end-to-end learning of block MDPs. There's many open questions in this area, such as improving our sample complexity and coming up with other models and positive results for end-to-end learning of block MDPs. Thank you for listening.